Some of you folks are hardware people, some of you folks are, well, you play with the sand, some of you folks are software people, play with your bits. I'm something worse, I'm a theory person. I play with imaginary things. They don't really exist until you come up with experiments like a traveling salesperson I'll handle here. Talked about adaptive system programming or the random world of artificial life. And what is artificial life? Well, it's a technique that applies Darwinian evolution to generate a solution or create a simulation of an environment. And once evolved, life forms become static, solution to a problem. So you can plug them into whatever program you need to plug them into. So when do you want to use it? When you know how to program the problem, but not necessarily the solution. And you know what a good solution, how a good solution should behave, and you can rank it or give it a fitness. And when you want to simulate the emergence of a behavior. Now here's the grand disclaimer. It's probably approximately correct, which sounds like a Microsoft paradigm, but this is what it is technically, is the best solution is not guaranteed. I mean, you can get it, and the example I use, I do get it, fortunately. Good solution is not necessarily guaranteed, but you will probably get a workable solution if everything is working right. So that's what you can expect and hope for the best. And what really constrains you is local optima. You're basically searching through a multi-dimensional search space of solutions, and it's not linear. You can get trapped in a location where to get to that next level, you're going to get less fitness. To visualize that, I'll just throw up this Conway's Game of Life. This is it's a grid and there's some dots there, and the dots, the rule is if there's two or three surrounding the dot, it stays on. If there's more, there's too much resources being used, it gets shut off. And this visually, in an abstract way, shows how it kind of searches the search space. If you imagine your optimal solution is somewhere down in that corner, this thing is working its best to find it, but it may not get there. In fact, I'll just stop this and go to one where it needs to run about 3,000 more generations before it gets to the end. And here is the final state. It hasn't really reached that area, so it's got stuck in local optima, basically. It's an abstract visualization of what I'm talking about when I say local optima. Get back to this. So how do you get past this? Well, iteration, repetition, and repeat it some more. The more reps you do, the more probable you'll get a decent solution. So types and environments and problems. You have your simulations where you have like economic trade. You use prisoner's dilemma to model trade negotiations. Do you cooperate with a person? Do you defect against them? There's biological, where they're looking for flocking behavior. If you have a bunch of sheep and some wolves, do the sheep learn to flock together to keep the wolves at bay? Or one of my term papers was virtual politicians, where you can tax, spend, campaign. You have a budget that you can't go below zero. There's a virtual Graham-Rugman Act, basically, there in your popularity, and try to find a balance in between. Now, for optimizations, you can optimize formulas, or my favorite is virtual robots. You know how to program a robot on a grid is fairly simple and straightforward in inputs, and you don't have to know how the actual operating system works because you're just going to evolve that. And traveling salesperson problem, which is the case study here. Now, fitness functions. In a simulation, it may be health points, like your sheep. Does it get bit by a wolf, then it is fewer points. Something like virtual politician, your popularity. Virtual robots, final scores. If you're stacking boxes, it's the number of boxes with the number of box sides against the wall or other boxes. And my favorite is temperature. This was kind of a unique experiment done by a chip manufacturer. They wanted to find a test configuration for trying to see, for quality control. They wanted to see how hot they could get their chips. And then when they took samples off the line, they wanted to use a set pattern to see how hot the chips got if they passed inspection, because heat is the killer in the chips. So all they did was just stick a thermometer on there and ran these codes, and the ones that heated up the most, they got the better fitnesses, and they survived to the next generation. So types of life forms. There's string evolvers. They're linear, they're not logic branching. Like the virtual politicians are, it's just a list of decisions, like this happens, this happens, this happens, this happens. And then decision trees or reverse Polish notation, which is something that early evolutionary programming used because it kind of came out of the math field, and this is what mathematicians use for describing their decision trees. It's very elegant, but excruciatingly hard, or takes a lot of computation to run this, because you have nodes, basically linked lists, and it's a lot of overhead to keep track of everything. And then finally, I throw out Isaac structures. You have a memory, you have a list of instructions, and a list of instructions is what's mutated. And A and B fields just point to values in the memory, and they're evaluated with an equation. And if it comes out true, then you do whatever instruction is in C, and if that happens to be a jump statement, your program counter is set to whatever value is in D. I mean, I like this. I'm biased because I developed it. But it is 1,000 times faster than decision trees, and that's why I could hang with the big boys at Iowa State when I was running a 5x86 133, and they had server farms. I just had a little bit more efficiency to my programs. So evolutionary operators. Everything comes down to the random number generator. Your population is initialized just with random values, and you mutate, with your random values as well. And then once you have your population, you test the population in your environment, and you rank it by fitness. And instead of sorting the whole population, it's just easier to do groups of 4. Computationally speaking, it's easier to do groups of 4. Top 2 are the better fitness, the bottom 2 are worse fitness, and you copy the top 2 over the bottom 2. So you have children, then you mutate these child genes, so there's some variation there, so they're not exactly like their parents. And you can use crossover, especially with like string evolvers. It's real easy that you just line them up, pick a section from the child A and child B, and just swap that section, and you have genes from both parents in both child, like mother, dad, and kids would have. Now, case study, traveling salesperson problem. It's basically optimize a circular route between cities. You end up where you started from. You have to visit each city at least once, and their fitness function is just minimize the cost, whether it's the distance or airfare or whatever you put in your data or set. And the gene type is a modified string evolver. Basically, it's just a list of cities, And for length, I did the worst case scenario. I said number of cities times number of cities minus 1, which is 10 times more than what you need, it turns out. Each gene is a list of cities. Gene must contain every city in it, and the city can't be visited twice, but that's enforced when you evaluate it. Because this one, your gene that's expressed, the actual behavior, is not exactly what the gene is in the code. You can ignore 2 of the same cities side by side and such. So there's a difference between genotype and phenotype here, which don't always get with string evolvers. This is the data set I used, just 11 cities. I wanted to make it a little more difficult so that you couldn't always just come right back the same way you went. And it was hard to, programming-wise or fitness-wise, to enforce that you had to be able to come back, or you had to visit every city, but some cities didn't lead to another city. So I chose to instead make it almost infinitely more, or infinite distance between cities. I figured like 10 times the normal value was close enough to infinity to have evolutionary pressure to get rid of those. And this is the program I used. I wrote it in Java, so it loads the last data set. And you can choose your iterations. That does 12 runs where you start with a random population and you go through however many generations. And you can vary your population size and the mutation rate. And mutation rate is basically you go down each of the child genes and random number between 1 and 100. If it's equal to or less than your mutation rate, then you change that gene with a random number. And per mutation type is 2. I can't use crossover because I need to guarantee that every gene has at least every city is contained in the gene at least once. It's, again, computationally expensive to take 2 children, swap, and then go through and check. And so instead of that, I just take sections of the one gene and move it to a different area. Randomly select the size of the chunk and move it around. So this is a baseline result. It gives me, it was generations, 1,200 generation, population 800, gene length 110. And ironically, right off the bat, this is the best score right there, the 9602. But it also didn't always get that good of a score. And down clear at the last one is another 9602. It's a circular list, so they do match up if you just move them so they line up, which is good. Otherwise, there'd be an error in the program. And this is the histogram of it. Shows that 2 genes got the 9602, 2 genes got 9603. When you're dealing with a distance of 9,600, the distance of 1 mile really doesn't matter. So they're practically the best answer, or can be considered the best answer, either one. So I went on to experiment. Here we have generations out to 12,000 instead of 1,200. Still didn't get any more of the good genes. Got a few more of the moderately good genes. And population size up to 2,000. Got a few more good genes show up. And then at generations of 12,000 and a population of 10,000, I got 6 good genes and a few other things, but this is computationally very expensive, so it'd be nice to find a configuration that didn't take up quite so much resources from the computer. I mean, the data set is small, so I'm saying it's computationally expensive, but for the size of the data, it was very expensive. And if you want to scale up, you want to find a different way of doing it. So I tried testing gene length 14, because I noticed that no matter what experiment I did, the evolutionary pressure was to crush everything down to just 11 cities. It never had to go back and go to another city route in it. It always ended up 11 cities, so I knew a gene length of 14 would have a good chance of being what I was looking for, and it turned out right off the bat, even at 1,200, it's 1/10 the generations, and 800 instead of 10,000, less than 1/10 the number of genes in the population. All of a sudden, you got 8 good genes and 3 pretty good genes, or nearly the same genes. So all of a sudden, it was like looking great. I had length 14 for 6,000 generations, got 10 out of 12. Thought, well, let's try this at 12,000. Well, bad luck. This is you're probably approximately correct, hitting you. Because all of a sudden, not quite as good. So another wake-up call, it's you're still dealing with a little bit of uncertainty. And I tried permutation only, and it did fairly well. Then mutation only, not quite so good. So permutation is probably where you want to go with your evolutionary operators, but mutation's good too, when in combination with the other. So pitfalls, anomalous pixie genes is what I call them. If there's any weakness in your code, it will find it. There was a for loop I cut off one too early, and I ended up getting results that were one less than what they should be. This on a data set of 4, so I could actually pencil it out and figure out there was something wrong here. And for days it took me to figure it out, and that was it. It had the final gene was the same, or final city was the same as the first city, and I automatically just added the last city to the first city because of the circle list, and if it's the same city, it's -1. And it was some little detail like that that just got me rather frustrated for 24 hours. And then debugging is another pitfall. You can have bad syntax, you can have bad theory, bad design where it doesn't quite match the theory, and then you can have bad luck, like in the 12,000 generation test. So final comments. Artificial life and genetic programming works best when you know how to code the problem better than the solution. And use it when probably approximately correct is good enough. Like traveling salesperson problem, if I was writing code for the landing algorithm of an Airbus A380, not so good. You don't want probably approximately correct in that case. So. And finally, don't assume anything or APGs will get you in the end. So that's my speech on A-Life.
Questions, anybody? So something like this, I do. So I can't pretend to understand most of what you talked about. It's pretty advanced. But something like this, like the traveling salesperson, you could do the same thing with, say, like UPS driving around town.
Yeah.
You have all these streets. And so would you say, like, to get to your solution, you try every possible way to get there, and then you get the best solution out of that?
Well, you mean the brute force search versus artificial life. With 11 cities, it's not that bad a brute force search. 10,000 cities, yes, it would be. So scale-wise, as it scales up, then the search space, A-Life takes advantage of a few of these symmetries and whatnot. Brute force search is good if you absolutely do want to know the best answer.
Sure. So this is getting the approximate answer, but
yeah.
the best answer would be the brute force
Yeah, the brute force search guarantees you your good answer, and probably approximately correct. Doesn't always just apply to a life. It does apply to your other learning algorithms, and for some reason I can't think of basic terminology right now, but you're and I've taken.
What's the best application you've seen?
A lot of scheduling things. There was a guy who patented using artificial life for time, optimizing time, so that kind of put a kibosh on using it commercially, but in academics, there's a lot of scheduling, like when you turn on a power station, you have to schedule that ahead of time, even though there may be storms come through or whatever, your windmills stop generating one day. But there's use of it to do time schedules for turning on power stations so that they could have them up and running and bring other ones down for maintenance or whatever. And it was hard to do brute force wise, or so they used this algorithm. And like there's a Tartarus example. It's not a real world application. It's basically a 10 by 10 grid, has a virtual bulldozer, 6 boxes that are randomly placed in this board, and you're supposed to push the boxes up against the wall. It's a rather difficult thing to solve. You have these inputs as sensor inputs from around the bulldozer, and the original guy who developed it said you'd never score over an average of 4.6, and he was the one of the early ones in genetic programming, so everybody believed him. Then I was at Iowa State, and then it's like, wait, we're getting 6s. So the professor at Iowa State said, you'll never get better than 8, and I used Isaac on it and got 8.2. And I don't think he really believed, well, when he read it, I made the joke that, well, I just added 5 at the end to make up for rounding errors, and probably not a good time to make a joke right then, because it was 2 years later that he actually redid my paper. Replication of a paper is, gold in research, and he came up with similar results. And granted, I've been letting a computer run entire weekends while I was gone to come up with the 8.2, but it was only like 62 instructions long and in the end, so it really wasn't that big a solution. It's just hard to find in all the noise. So, and yeah.
I'm curious. I'm a driver. I'm trimming boxes in my truck every day. They've all been scanned. They all have an address. It's different every day. Do I just get a printout and start driving?
Yeah, right.
Probably not. There's something that's got to tell you your problem.
Something like this, it's if you're using less computer cycles to come up with an answer quicker, you're going to get the best answer that you can get in the CPU time you're going to use to pick the best route for the day.
Yeah.
I have a question.
Okay.
Your algorithm is basically limiting the amount of guesses that it has, essentially, right?
Well, it builds on the ones that show promise, basically. If you increase the fitness, that's what it looks at. And then,
You made quite a few comments in your presentation about using up a great amount of computer time. And with your different graphs you had on there, you had like your 1,200 and your 12,000 generations.
yeah.
You're essentially just limiting your amount of computer time to get the best answer, right? Instead of going the brute force route.
Yeah, I mean, the reason for doing the searches on versus like 6,000 generations versus 12,000 is if you're going to use this algorithm again on a different data set, you want to kind of have some idea of what to target. And it does build on, like, it starts out completely random. Any gene that shows some promise will get a better fitness, and it's saved for that generation. And its children, there is a good chance that when you mutate it, it's going to be worse, but there's always that small chance it's going to be better. So it builds on where it...
For your city, a good explanation. You had 4 cities, 2 of them were 900, 2 of them were 1,200. The 2 900s would stay, the 2 of 1,200s would go away, right?
Yeah, or if had paths that were the 1,200, if matched up against a pair of 900 distance routes versus a pair of 1,200, the 1,200 get deleted and get replaced with children.
So you just progressively get a better answer.
Yeah, it's like selective breeding of, cattle or dogs or whatever animal you want to insert here.
That right there is explaining more about what you did.
It's based on biology. The research group I was with at Iowa State was a loose collection of people who showed up every week in a room kind of like this. People from different disciplines. You had philosophy majors who say, well, is an artificial life form an actual life form? Should we be killing them? And it's like... Yeah, oh God, do not use the word mental model around a psychology major, because that means so many things to them, and it's so. Yeah, well, I wanted to say the philosophy people that I save the random number seed to every experiment, and it's not, and every time I do one, I can replicate it again, so these life forms aren't just, I can replace them with exact copies of what they were before, but if I... That's a whole other issue. But, so all it is an algorithm that you can, that these creatures have been generated by, but if I lost that random number seed, I would never be able to make this again, so maybe they are alive. So if you think of the Big Bang, if you know exactly what the configuration is at the Big Bang, you can replicate the universe all over again. But if whoever was doing the Big Bang lost the random number seed, then we're actual life forms and not deterministic life form. I wanted to mess with the philosophy major with that one. Yeah, this part gets edited out.
So how far away is this theory from 1,200 monkeys and keyboards composing the entire works of Shakespeare?
Oddly enough, well, if you throw in compression algorithm, it's like 10,000 times easier to come up with the complete works of Shakespeare because your search space is that much smaller. So once the monkey does its draft of the works of Shakespeare, if it gets closer, then that monkey's bred with another one that came closer, and then child gets to continue on the family tradition. In one regard. Yeah. They're just random, then start from random scratch again if you keep the same monkey. Yeah.
So who developed this system?
Koza, a mathematician, one of them was Koza from, I'm trying to think of it, started in the 80s or whatever, and his star grad student was Astro Teller. He's the one who came up with Tartarus, so he'll be the one who punches me in the eye when I say, yeah, 4.6 right. But, so it's gotten influences from biology, and there's, my paper ended up rewritten by my professor, but that's how it works in academics. He has a PhD, I have no credentials, so his name comes first, my name comes second, and in the first paragraph it says I invented it, so I'm happy with that. And that was published in GP 98, which was a conference in Madison, Wisconsin at the time. It floats around the country, so there are people actively using it. It was taught in math at Iowa State till that math professor moved to Canada, so I think it's still being done up in Canada by him. So my Isaac structures are chapter 12 of his textbook, and VIP is the virtual politicians is towards the back of chapter 2 in his textbook. So I promote him in that, and I don't get a royalty, but at least I get my name out there somehow.